Wonderful. Wonderful. Thank you.
Um, so welcome to this webinar on AI for digital repositories. It's a Fidelis webinar, so I'd like to first introduce Fidelis to you in a few words. So what is Fidelis? Fidelis is a project that tries to enhance EOS sustainability by establishing mostly a network, and not just a network of trustworthy data repositories. The idea is that we make the research data landscape in Europe more fair, and with that also more trustworthy, and that's what Fidelis is all about. So it does that by setting up this network, and with that also foster harmonization around repositories. So it does that by developing a T-term matrix. So if you've heard of Fidelis, you probably have heard of T-term matrix already. And that is really to help repositories to become more trustworthy and therefore also more fair and interoperable. As a third objective, we try to strengthen repositories by an active training and support program. This webinar is part of that training and support program. It's much broader than that. We have different ways of how we try to support the members of the network in making their repositories more trustworthy. Oops. So it's a very diverse consortium of very diverse partners, different institutions, different universities from all over Europe in a very wide range of domains. So with that, it's really this entire project is really represented by a very diverse research landscape in Europe. Before we go into more details regarding this webinar, I have a few questions for you, just to get a bit of an idea of who's in the room. So for that, I will stop sharing my screen, and then Anja can share her screen to ask you a few questions. Okay, so this the questions we'd like to ask you through Menti. You might have seen it before. So you can join this session by going to menti.com and use the code above, or scan the QR code on the bottom left of the screen. So this is just to get a bit of an idea of who we have. So the first question is the simple one, I suppose. In which country are you based?
Please scan the video. You need to scan? Yes. Okay. But I try. I cannot.
All right. I see quite a few people from Germany, UK, from the Netherlands. That's great. Oh, Canada even. Overseas. From Scotland. Monaco even. All right, so we have super broad representation from all over Europe and beyond even. It's really nice to see. It's great. All right, for me, you can go to the next one. Thanks a lot. To get an idea of what you are doing at a daily basis in terms of work, we'd like to know what describes your professional role at the moment. All right. Well, mostly repository managers and curators. That's great because, well, it is for the entire range of people being involved in repositories, of course, but repository management and curators are the main audiences. That's super nice. Great. Well, thanks a lot. So now we have a bit of an idea. So mostly repository managers and data managers. So the last one I have for you for now is, are you affiliated with Fidelis at all? And I see a lot of no's, which is great, because that also means that we have very nice coverage also outside the primary, let's say, members. That's what really was what we were aiming for. So super nice to see that. Perfect. So by far, most of you are not affiliated with Fidelis. Great. Then I will shortly introduce the sessions, and then we can really go to the actual presentations. Interesting stuff. Share my screen again. So the webinar will consist out of two parts. First of all, we have a presentation session where we have some, I think, very nice presentations about usage of artificial intelligence in digital repositories. So a bit of theoretical background about what the main concepts are in artificial intelligence, and then some, I think, very nice examples of how artificial intelligence can be put to use to make a repository mostly more useful for the end user. So that will be recorded. Like this is already recorded. There's very limited time for questions regarding the presentations themselves. So because we also have a very large group of people, as you might have noticed. So if you have any specific questions regarding the different presentations, please ask them in the document. The link to the document will be shared or is already shared in the chat. This will be followed by a parallel session, so you can choose what you want to join. So you can either join a tutorial, and that will be a tutorial on very basics on how to use mostly large language model tools related to data. And the second parallel session will be a discussion where we have some statements, propositions, if you like, that we will be, where we thought that would be interesting to discuss because we hear a lot of different opinions about these topics. So we have 30 minutes for that. The presentations will be available after the webinar in PDF format, and I think it was already mentioned in the chat. Again, we have a big group. We have a regular Zoom room, as you have seen. So not like the webinar type of Zoom room. So that means that we ask you to please mute when you're not speaking. So this will be the schedule for today. So we have three very interesting speakers. We have first a presentation by Anna Claudia Sima, who is the team lead of the knowledge representation unit at the Swiss Institute of Bioinformatics. They do a lot with, of course, knowledge representation, so knowledge graphs, but also large language models, and apply them to data. Then we have a presentation by both Séverine Duvaux and Damian Claricic, if I pronounce your last name well. Apologies about that, Damian. Where they will present some actual use cases on how they use artificial intelligence to make their repository and better user multi-channel, of course. Then we will have Claudia Sima, who will give a short presentation about how they are applying artificial intelligence at the EOSC Data Commons project. Got to say a few words about Severin and Damian. Severin is the team lead of the biodata resources at the SIB. Damian is the resource manager of a quite well-known resource in the life sciences, at least named String. Yeah, I think that was my, oh no, so and then of course we go on to the parallel session. So you can choose yourself which one you'd like to join. So you either join the discussion or you join the tutorial on leveraging LLMs for repositories. Note that that involves coding. It will be live coding, so somebody will tell you, it will actually be Anna, will tell you on how these different tools can be used. If you're totally not into these things, maybe it's better to join discussion, or of course the other way around. Then we will wrap up and well, hopefully look back at a interesting webinar. Okay, then I stop sharing and I'd like to give the word to Anna.
Thank you very much. Thank you, Gert, and welcome everyone to this webinar, and thank you for taking the time to join us. I would like to start by introducing some concepts around large language models in the context of digital repositories. But before I do so, I would like to just say a few words about our unit. So I co-lead the knowledge representation unit at SIP, where we do research and development around data and knowledge modeling, and a lot about knowledge graphs, ontology engineering, and semantic search, which is why on the broad topic of AI in data repositories or digital repositories, I will focus this talk mostly on the semantic search aspects. So we aim to facilitate data access by both people and services. We often talk about machine actionability, and this is what we aim to do as well. And we are involved across EOSC FIDELIS, Eden, and the EOSC Data Commons projects. So today I will try to also talk about how these projects synergize. And in a nutshell, knowledge representation serves as the language through which we communicate with AI systems. And I think that's also the context in which we will start the discussion today. So the goals for today's webinar are to have a high-level understanding of LLM concepts. For some of you, this will already be familiar, but maybe for some it will be new. And to see their applications. As I mentioned, this is a broad topic, so we will focus on semantic search within and across repositories, and we will try to not only give a theory about this, but also illustrate some concrete use cases that we have with XPG-GPT, String Chat, and to foster collaboration, as I mentioned, by also introducing the EOSC Data Commons and the work that we do there. But first, what is a large language model? It is a deep learning model trained to predict at a high level the next word in a sentence based on a large corpus of text. So if you have a text like nothing is impossible, even the word impossible says I'm possible. If you prompt a large language model with the words nothing is, it is supposed to predict based on the corpus impossible. The way it is trained at a high level is through a very large scale fill in the blanks exercise, if you will. So the model learns to always predict accurately the next word given a text that is being trained on. And it's very powerful because it's self-supervised. So you don't need actual labels to do this training. There are a few steps in the process. It's good to know them in principle, and probably some of you already do. Pre-training, fine-tuning, retrieve and augment, and finally, it's always good to also validate and evaluate what you use for your purpose. I will very briefly mention the very first step, which is tokenization. The reason I bring this up is because we hear a lot about tokens, and what are they? So it's, you know that this is what you pay for when you use a commercial LLM, so you pay per token. But it's actually the way that LLMs break down sentences into smaller pieces, not necessarily words. Sometimes it's fragments of words, but it is sort of the vocabulary of an LLM. And if you're curious to find out more about this, there are places where you can use different tokenizers and see how sentences get split. So for example, we can compare two here for just this nice sentence, hello and welcome to this webinar. And perhaps you might be surprised that you have quite different ranges of, for example, number of tokens, depending on the tokenizer that you use and implicitly on the large language model that you use. And this is the first step in the processing of text when you use a large language model behind the scenes. Now, of course, the vocabulary by itself, the tokens, do not actually have meaning. They are just words or pieces of words. So the central part in any semantic search system, but also in specifically large language models, is so-called embeddings. And you might have heard about this, but embeddings are a way to transform tokens into numbers while preserving their meaning. So I have taken an example here, which I think is relatively easy to understand, where we have 5 example words, and we would like to have a way to represent them, which still kind of captures what they mean. So we could have these 3 sort of number vector representations, which capture, for example, if the word is a fruit, how likely is it to be a fruit? Well, for banana and orange, the first and the second word, this is very likely. However, for yellow, for example, this is not the case. So it is a number, let's say between 0 and 1, that will capture the probability that the word has a certain meaning. However, what you see here is a simplification. These are very large vectors that have been learned from text, so we cannot really recover exactly what these vectors mean, but it is the way that the machine learning system in general and the LLM in particular learns how to attribute meaning to different tokens. So it goes from text to numbers, which can then be used in semantic search. Now, one thing that you might notice here is that words are still ambiguous, so their meaning will be dependent on the context. And this is where we get to the part that you might also have heard of, which is attention, which is a mechanism to capture the meaning of words in their context. So for example, if we have a sentence like the girl and the boy walked home, she, attention is a way to capture the idea that the word she refers to the girl and not other words in the sentence. And this is also learned by training on a very large corpus. And of course, it might happen that training on certain corpuses of text can also lead to biases in the data. So attention is also a mechanism that allows you to see whether this happens. So for example, in a sentence like, the doctor asked the nurse a question, if you follow it by he or she, it might be ambiguous what is who. But I'm just presenting this at a very high level because I think it's good to keep in mind that LLMs learn the meaning of words in context. Now, skipping very quickly through these steps, what is the result and what we all are familiar with are foundation models. So this is, for example, the GPT family of models, which can be used then for different tasks. And of course, this is also very relevant in the context of digital repositories. where you can use foundation models, for example, for summarization, for question answering, and so on. But usually what you do is not taking a foundation model as is, but rather, for example, fine-tuning it. And here is where we get to the example of ChatGPT, which was initially based on GPT 3.5. And actually, ChatGPT is a fine-tuned version of a model because it has been trained to answer questions. This is not necessarily the default. So if you use a foundation model that hasn't been fine-tuned specifically for this purpose, just predicting the next word is not a guarantee that a model will predict an answer to a question. Maybe it will predict another question and so on. So ChatGPT was also fine-tuned. And the secret sauce, and something that is important to emphasize, is it was fine-tuned via human feedback. So quite a lot of human curation was also put into fine-tuning ChatGPT. And this is true for all of the models because the quality of the data that they are trained on and the fine-tuning through which you can block out negative behavior, for example, are key to the success of these models. So the role of curation still remains extremely important. This is also detailed by OpenAI. So there's a lot of mention about the labelers that have been used also for demonstrating outputs and for ranking outputs. So the quality of the underlying data and the curation effort is something that is very relevant to large language models as well. Now, what is the end result? We all know it. The famous line where you can ask anything. So where should we begin? What is the meaning of life? Seems like a good question to start with. So it's this model that can answer any question and that all of us have started using on a day-to-day basis, which leads to the question, all right, so we have these very large models. Are they all we need now? Can we discard, for example, all the past databases that have been collected and curated over the years, because now LLMs are everything we need? And if you would have asked this question a year ago, probably there would have been suspicious half-half kind of answer from any given crowd. Today, I think it's relatively clear that LLMs have a lot of pitfalls and limitations as well. In particular, one which has been known from the very beginning is the problem of hallucination. So when they are wrong, they are confidently wrong, and you have to always validate their answers. But there is also the problem of cutoff date. So large language models are expensive to train, so they are trained periodically on the available data, but beyond the cutoff date, the model by itself does not have access to knowledge if you don't complement it with something else. Of course, the cost is a very big factor in this. This is why you cannot afford to retrain very often. And there are also environmental considerations to think about, both for training and for using large language models. Privacy is a relatively well-known concern. You shouldn't put private information in commercial models. But there are also others, such as lack of interpretability, lack of provenance. So where does an answer come from? You can never really be sure. And lack of actionability. So an LLM by itself cannot actually perform something on the environment. It needs tools to do this, bias, and so on. So considering this, both positive and negative aspects of LLM, what is then the role of digital repositories in this? Well, LLMs are a powerful interface. So they are much more powerful when augmented with facts that can be retrieved from a curated external database, as well as tools, so services that can be accessed, for example, via APIs. And the way that LLMs can discover these is via so-called model context protocol servers, where existing service providers can expose APIs to LLM so-called agents so that they can be also accessed via natural language, which makes them more powerful, easier to use, and so on. And if we look at this picture, it is fairly straightforward to see that digital repositories can provide both data and tools in the form of, for example, APIs, in order to facilitate the access to data for casual users via LLMs. So what we will talk about in the next parts of the webinar will be concrete use cases that show exactly how this can be achieved through some examples at the SIB. There are two possible ways that we can go about this. One is the so-called retrieval augmented generation, RAG, where the first step is basically to identify what information you would like an LLM to be able to search through. This information can then be embedded in a vector database. And when a user asks a question, the embedded information can be searched through in order to find the relevant context. And then the prompt that you would feed to an LLM would be augmented with this context in order to generate new answers. The examples that you will see in this direction are XFuzzy GPT and the EOSC Data Commons. Then for any additional analytics tools or for frequently updated data, which you cannot really index as often, you can use the APIs to access this data via an MCP. So for this purpose, you can describe the APIs in a natural language fashion in an NCP server. And then for each new user query, an LLM will invoke the appropriate tool, which will then trigger the appropriate API call. And this will be the example that you see with String Chat. And this concludes the overview of the introduction to LLMs. And I would like to then pass the word to Severin in order to present XFuzzy GPT.
Okay.
Thank you.
Thank you, Anna. So I'm going to share my screen. Yes. So hi, everyone. Thank you, Anna, for the nice presentation. Mine will be far less technical, but I would like in this next 10 minutes present you a new service that we released recently. So its name is XFuzzy GPT, and this is one example of the use of LLMs to enable access to structured biological knowledge using natural language. So my name is Séverine Duvaux, and together with Damien, Anna, and Gert, we work for Swiss Institute of Bioinformatics, which is a non-profit and independent institution which forms a network of 900 scientists, among which 200 are employees. So the mission of the SIB members is, among other things, to provide the scientific community with high-quality repositories and software tools. Founded in 1993, as a protein sequence analysis platform, XFuzzy was one of the first websites in the world. It was transformed into a catalog in 2011. Currently, there are 168 software tools and repositories listed in the XFuzzy catalog. So on the right, you can see XFuzzy homepage with a search bar at the top. The search in XFuzzy uses a keyword-based or a Google-like, if you will, approach. So the XPC search engine enables to search the catalog and also to run APIs query in parallel on different repositories. This is what we call the meta search. So let's see an example of a meta search for a user, let's say interested in the lactase, a protein. From the XPC search result page, they can access UniProt to discover, for instance, the function of the protein in human or to download its sequence. If they want to know in which species the gene exists, they can go to Swiss Orthology. If they want to see in which tissue the gene is expressed in human, they can rely on BG. And lastly, if they want to visualize the 3D structure of the protein, they can access Swiss Model. This is how a meta search result page looks like in XPC. So this is the 4 databases or repositories I was mentioning before. So while this approach has some merits, it is not fully satisfactory because it is based on silos and it requires that the users know exactly where they can find the information they need. Moreover, integrating data from multiple sources requires manual processing and a consolidation of the results. So nowadays, technologies enable us to simplify this thanks to conversational agents like this one, where users can ask questions in natural language and get responses in human readable format. And this is the objective of XPC GPT, a new service that we released in April 2025 and that will soon replace the current search in XPC. It enables natural language queries across distributed biological data. XPC GPT offers a streamlined, chat-like experience. But behind this simplicity must lie a solid foundation based on structured, machine-readable data. For this, we have chosen to use the semantic web approach. I'm not going to explain you what semantic web is because we have eminent experts in the audience and especially among the speakers. That's why I'm going to present you the semantic web as information represented as triples. Triples consisting of a subject, a predicate, and an object. If this sounds too complex, just consider it like a simple sentence like Bern is the capital of Switzerland. Subject, Bern is capital of, predicate, Switzerland, object. Now, if you link triples together, you can form what we call a knowledge graph. This is an example of a knowledge graph about science fiction movie. It is composed of triples like this one. Leonard Nimoy played Spock, or Obi-Wan Kenobi is a character in Star Wars. If the repositories providing the knowledge graphs are interoperable, we talk about federated knowledge graphs. The federated knowledge graphs can be queried using Sparkle, a query language enabling to run queries that span several knowledge graphs. As a result, thanks to Sparkle, users can perform queries which cannot be answered with the usual text-based approach. An example could be retrieve genes expressed in the mouse brain which have orthologs involved in human glioblastoma. This is very powerful, but the Sparkle syntax is very hard. So this is an example of a Sparkle query. So without a very sharp expertise in semantic web and Sparkle, it is very hard to create a Sparkle query by yourself. That's where the usefulness of AI comes to play. So after the release of ChatGPT, so a few months after that, in April 2023, my colleagues, Ana Claudia and her colleague Tarcisio Mendes de Farias, explored the possibility to use LLMs to transform user questions in natural language to Sparkle queries. And their findings were promising enough so that we started to implement it in explicit GPT. Currently, explicit GPT supports 6 federated knowledge graphs: BG for the gene expression, RIA for the biochemical reactions, Swiss lipids for the lipids, Cellosaurus for the cell lines, Swiss orthology for the orthology, and UniProt for everything related to proteins. This is the XPC user interface. You can see on the left, the user can ask a question in natural language, and this is the result page they obtain. First, the whole process conducting to the Sparkle queries is described in order to build trust and transparency. Then the Sparkle query is displayed and it is also explained. If a user wants to run the query on the knowledge graph itself and see the raw result, they can do that by clicking on the button. And at the end of the page, the results are summarized in human readable format. So to wrap up, with explicit GPT, users have, with no technical expertise, have a simplified access to a powerful but very complex technology, thanks to a very lean and intuitive interface. The databases providing the knowledge graphs used by explicit GPT are not only of high quality, they are also regularly updated, which is very important, as Anna explained, in the context of LLM. And thanks to a rich ecosystem of metadata, which have been standardized among the knowledge graphs used by explicit GPT, and also thanks to more than 1,000 example queries, which link user questions in natural language with their corresponding Sparkle queries, the accuracy of the responses is high and the hallucinations are mitigated. So I'd like to conclude my short presentation by saying that explicit GPT offers users the best of two worlds: the simplicity of LLMs combined with the power and expressivity of Sparkle while minimizing hallucination. So now I'm leaving the floor to my colleague Damian, and I thank you for your attention.
Hi, do you hear me? Yeah, I guess so. So let's take this out. Okay, we have to live with that. Okay, so I will talk about how MCP servers work. This is another way to kind of how to communicate data to the AI agent. So you can, so the model has some internal knowledge, which is basically the text it was trained on. So it can answer questions like, what is the exact time when the World War II started, and it will say something, but it cannot say what time is it now, primarily because it doesn't know your location, but also because it is not model. But it actually does. If you ask chat what is time in Zurich now, it will answer something and it will be correct. So how does it do it? So user asks the questions, what is the time in Zurich? Agents takes it and knows for such a question that it should create a very particular structured data within its response. It's like it's talking to you, but actually it's some XML or whatever code. Sometimes when something goes wrong, you can see actually within your response those calls. And so it will be like that. Oh, I open some bracket, get current time with some arguments, for example, with the time zone. And then the runtime environment which agent operates in, called controller, sees that call. It doesn't allow you to see it, but it sees it, and then runs the tool corresponding to that particular call. So it is get current time, so it runs, for example, some Python code, and then this tool outputs some information, the time exactly. This is then taken, the output of the tool is taken by the controller and inserted directly in the context of the agent, and the agent can just, in a human readable format, answer the questions correctly. So, for example, for American, it would translate from the 24 time to 12 hour time, so PM, AM. So, how does it know which tools to call? So this runtime environment, the controller at the beginning gives it a set of tools it can use. So, for example, one would be get current time. The other, would be web search. Whenever it searches something, is actually directly just generates this kind of call, web search, with the questions you ask, and it uses Google or Bing, and then the answers from that are directly injected in its context, and it can read it and answer your question. So how do we tap into that? So, for example, there's with our resource. So, for example, like you can ask what's the function of TP53, and it will answer correctly. However, what it cannot be embedded is the exact list of Go terms, which sometimes you may be used. Primarily because it's a long list, it is not trained on this data, and also because it may change from one day to the other. So it wouldn't be able to answer. So we want to tap into exactly that. How we do it? We want something like user tool registry. So for example, get the Go term for protein, and we want to communicate, hey, we have this list of tools. Please, if I ask questions related to these tools, please call them. And this is where MCP comes. So basically, this is a protocol, but more we use this. We don't mess with the protocol. We directly create the servers, which basically operates on this protocol, and it exposes the tools to the agent. It executes the calls that controller gave us, and processes and structures the return data. And these two are very critical here, and that's when kind of why they are popular recently, because you have absolute full control how the tools are called and how the data is processed. It is very important because you can change the data, truncate it, massage it so that it's useful in a way for the agent. And so how does it work? You ask some questions, the agent gets it. Then at the beginning of the session, the controller asks your MCP server, hey, what tools do you have? And the MCP server says, hey, I have like these Go terms tools, and then it inject into the agent context, so agent knows and is trained to primarily utilize these tools given your list. So it will, instead of answering from their own internal knowledge, it will always prefer to call the given tool. So it's a bias in that way. So the user asks what is the Go terms, and we notice that we ask here for TP53, but in the arguments we see that we only accept, for example, UniProt. And then agent, using the internal knowledge, would for some proteins would know actually how to translate those TP53 to UniProt, because that's often in the literature, so that they would know. For less known proteins, it may not know, but for the TP53, it will know, and it will then controller will notice that, and hands over the things to the call to the MCP, and the MCP knows exactly what to do. It, for example, goes to the internal database and gets the protein, and then the tool outputs the list, which then in return is injected into agent context, and agent parses this list and answers your question. So, and what is happening here? So that's that's why it's fun. So the MCP actually can, for example, you can run the database below it, and for example, have some Postgres and select statement, and then you will get the tools. But you can make it as complex, as fancy as you want. First, for example, you don't need to have your own database. You can directly go, for example, to Uniprot and just use the public API to get the data you want. So it doesn't need to be, you don't need to even own the resource to create MCP server for the resource. For example, before String did their own, there were 2 or 3 projects that already did the MCP server for the string. So you can, for example, use the public Uniprot API, and then MCP will just get this URL and put the data back to the agent. But of course, you can make it as fancy as possible. For example, you can chain the calls if the agent doesn't know how to translate to the Uniprot accession, then we can use Uniprot itself to translate Uniprot API to translate the protein into the internal code, and then get the information about the protein, and then we can create how many other tools we want on this output. For example, this output can say, okay, which are Go terms, the other, which is with what other proteins the protein interact, or what are the complexes it forms, and so on, so on. What is the structure? It can input the image, for example. And then, depending on the tool you create. So you can do fancy stuff. And this is all completely unrelated to Uniprot, because Uniprot has no idea what you are doing. And of course, also completely opaque to the agent. Agent knows, I just ask this question, I get the answer I get the answer from that resource for this question. So that's really cool. So, and this is all hidden just with the simple URL address. So the user doesn't need to know anything, that this URL gives a list of the tools and give the answers for the functions that are defined with this tool. So for the user, for agent, or for anyone, this is just a simple URL. They don't need to code anything and can directly start using it just with the URL. So this is just to reiterate, controller just communicate with the URL, and whatever happens under this URL is under your complete control. So that's it. That's as simple as goes. So again, very simple to implement, to integrate. There is intuitive user interaction and readable output. It's good for data exploration and summarization. And the agent can autonomously query multiple tools where needed. So it doesn't need to query one at a time. So there's one tool per question. It actually can query one tool or several. And then based on the output, it can internally query more of the tools. And then only then it will answer you. And works with existing infrastructure and API. So you don't have to even, as I said, you don't need to own the API or the resource. You can connect your resource, but use, for example, protein translation from another resource, like from Uniprot or String. And most APIs are already optimized for speed, so it is usually very fast. And you don't need to use API. You can, for example, with those tools, you can use any code that you write, including for statistical analysis, if you want. So you can then, for example, call first some resource, get the data, do some statistics, and then the statistic give to the agent if the tool says, look, compute the statistics for X. So not so good stuff is requires relatively large LLM to work well, because the agent has to understand all the tool's definition, not to be confused by it. This is all human, in the human readable language, those definition and parameters and definition of the parameters. And so this usage costs can be significant if you want to do a lot, thousands of these queries. Tools must have a clear, well-defined functions and parameters. So that's kind of the major drawback here, because LLM cannot arbitrarily dissect and restructure data, cannot like connect one big table to another big table. It's not good at it. It will lose some data. And so it's better that the data is a little bit like truncated for it to have reasonably good reasoning on it. Limited reproducibility because LLMs are not deterministic, and the context window, of course, is limited, so may truncate or drop information or crash if there is a lot of data. And of course, as with all of this, there's risk of hallucination and misinterpretation. So important thing is very good for exploratory research, but not for basically scientific validation. So, and as this was mentioned, I'm responsible for string. So our database is huge. We have more than 10,000 species, 20 billion interaction total. If we want to count all the kind of triples that we have within the database, so all the kind of basic atomic data points we have is probably around 200 billion of them. So it's really, so giving as a table is not particularly useful. And we have, of course, statistical tools in visualizations. So all of this data can be accessed under this URL. So you can put in your chat or in your Claude the URL, and it will communicate with string. There is a special box to it when in Claude is by default in your standard website in OpenAI, it's somewhere in the function. So you just put in URL and it will use string data and it will generate visualization. And this is open source, so you can take and you can look at the definition and use it in your own tools. And we implemented this as a showcase of this MCP. We implemented string chat. So basically, you can talk to string about the data and within the string website. So if you go to string website, there is a string chat, and you can talk to him about what are the interactions of TP53, and you have many examples, around 20-25 examples of the different questions you can ask. Okay, that's it. Thanks.
All right, thanks a lot, Damien. So then we continue to the last presentation about EOSC Data Commons by Anna.
Thank you. So I will continue now and go back to the context of EOSC. So I'm sorry, I'm not sure why this. All right. So what is the EOSC Data Commons? It is meant to be a platform for facilitating interdisciplinary data discovery, access, sharing, and reuse across the EOSC Federation. So it's quite an ambitious project and quite a technical project that wants to build an ecosystem that provides access to all the research outputs within the European EOSC space. And this means data sets and tools. The important keyword is trusted. So in the context of Fidelis, especially, there's a good connection to the idea of trustworthy repositories. And so to dive into this a little bit, we want to build together as a strong consortium, a one-stop shop for EOSC datasets and tools. The Data Commons project is part of the Innovative and Customizable Services for EOSC call, and it runs until end of March 2028. The consortium is very broad and multidisciplinary, which is one of the strong points, I think, of the project. So here I'm just listing the partners. They were too many to fit on a page, so I just put them, collated this a little bit, but we have across multiple disciplines, life sciences, earth and climate data, and so on, both providers of use cases and of tools, so a very strong consortium. In the interest of time, I will just mention that there are two main components. One is a part that will allow you to search for data and tools, and another one, so the first part is the matchmaker, which relies on repositories, data repositories, for dataset discovery, but also on tools, catalogs, and matches them together to be taken over by the data player, which will allow you to run analytics on this data with the tools. Now, fast forwarding a little bit, what is the role of AI? I will focus here on the steps that we have taken already in AI-based discovery of data. So the matchmaker is already advancing quite well. We have a platform that has been developed and it's already live. So I would like to just take 1 minute to show a demo of this because I think it's always useful to do that. So you can find it online, but essentially here is where you can search for data. I will not type in data, but I will try one of the examples that I already have. You can try others. You can search for data sets about certain topics or about certain articles, certain authors, and the system will search across all the metadata that has been indexed and will provide you with answers, the source of the answer. You can also view the original record, and you can further refine the query. So the more specific, the better. For example, if you want to search for data sets before a certain point in time, you can also do this. And you will have, a re-ranking based on AI, which will result in improved results. So here we don't see the result from previously because it was not one of the older than 2016. And you can further refine until you get to sort of the specific part that you are interested in. And you always get a summary of the data sets that are available in the platform. So this is part of the progress that has been made only since April this year. So it's, I think, very promising for what will be the future of this project and hopefully the vision of EOSC as a federation of repositories accessible through this platform. So you've seen a demo. How does this work? Well, essentially, we have the repositories. They provide APIs through which metadata crawlers can harvest metadata. This is harmonized and stored into a warehouse, on top of which an AI-based search engine at query time searches for the relevant entries and provides them to the user. I would like to conclude with a call for collaboration, because I think the success of each of the projects kind of depends on collaboration with the others. There are strong ties, we already know, between EOSC Fidelis and its sister project Eden. But I would like to point out that I really see this as a three-way collaboration where Fidelis is obviously the provider of trustworthy repositories. Eden will provide, curation and metadata guidelines. And all of these will benefit the EOS Data Commons in order to discover, share, and reuse research outputs within the EOSC space, hopefully materializing the vision of EOSC through the strong ties between the projects and through collaboration. So with this, I would like to thank you and conclude my talk, and I think we will continue with the next part. Thank you very much.
Right. Thanks a lot for all the speakers. I think you did well a great job in helping us to understand well what all those concepts mean, and then of course it's a field that changes like crazy fast. New concepts come and go all the time. But I hope also the audience got a feeling that well currently especially these examples are really kind of at the sweet spot on how mostly large language models in this case can really help making the data that is stored in these resource repositories more helpful. So as I mentioned in the chat, there's unfortunately no time for questions, but you're very much encouraged to, if you have any questions or remarks, to write them in the shared document, and also the speakers will try to address them during the meeting. Having said that, I'd like to go on to the second part of this meeting. And in the second part, we have two possibilities for you. So you can either discussion. So we have some statements we think are interesting to discuss for this audience, and we will start voting again. Then we have a short discussion about them, or you can join the tutorial, going a little bit deeper into okay, how would it work if I would like to use large language models for my data repository or database. So we have two breakout rooms. Breakout rooms are now open. So if you want to join the discussion, you can join the structured discussions breakout room. Just click the join button. All the way, you have to scroll down. If you click breakout rooms, then you scroll all the way down. So you can either join the structured discussion or the tutorial on leveraging large language models. All right. All right, welcome back. Just waiting for, oh, I think the breakout rooms are already closed. Does this mean that everybody should be back? No. Nope. Tutorial is still closed. Shouldn't take long. Starting in a few seconds. All right. And now everybody should be back in the room. Welcome back. I hope you had a nice session. Of course, well, you only had an hour and a half, and we tried to make it as interesting for everybody as possible. So might be a bit quick, but I hope also well we of course hope that you have learned something, and also with this discussion session we're able to put some thought into how AI can help us. This was really a very first attempt to do so, at least from the Fidelis part. The slides and the recording will be shared with you after the meeting. And in that same email, we will also ask your feedback about the session. So this is the very first time we're doing this. Also for the Fidelis project, these sessions are relatively new to us. So we're very curious about what you thought of the webinar and how we can improve. If you want to know more about Eden, Fidelis, and the Fidelis network, go to edenfidelis.eu. And if you didn't do that already, sign up for the newsletter to get updates on the training and support program. So also future events organized by Fidelis, you will get them in your mailbox. What I would like to notify you about is that already in respectively 6 and 8 days from now, we have 2 other very interesting workshops organized by Fidelis. One about legal challenges and one about policy checklist for fair enabling data. You're very welcome to join those. Registrations are still open. If I didn't forget to mention anything, then I would like to first of all thank the speakers a lot for their great talks. I hope everybody enjoyed them. And of course, I would like to thank you a lot for your participation and sitting through the end of this session. And we hope to see you again in the future sessions, anything related to Fidelis or in